So this is, as I said, one of a series of lectures. Others that we would like to work to develop amongst the advisory committee and Rebecca as well is sort of statistical modeling and AI. We'll touch a little bit about it in this presentation, but for the sake of time, I haven't been able to go into a huge amount of detail around that. And I think that there are other people who are eminently more qualified than I am to talk about statistics in AI and how it works. Archives in AI is another one. So looking at the application of AI throughout the archival life cycle, if you will. So from the point of records management all the way to the point of access. And without losing sight of the fact that artificial intelligence is record. So it is a historical record in and of itself because governments are using this to make decisions. And then ethics and archives. So the emphasis really is from the archival perspective, and that is the perspective I will be speaking from during the course of this presentation. So looking at this very much from its application, particularly, as I said earlier, given my background around appraisal and selection and sensitivity review. And the things we also need to think about when we look at artificial intelligence as a record, a historical record in and of itself. And for those of us, because I worked in government, I'll also be just looking at this from the perspective of public sector accountability and transparency, and sort of the questions we need to ask from a policy perspective around the application of AI and policy decisions. And also because a lot of these policy decisions will affect us as citizens. So are there ways that we can more intelligently engage in these types of discussions around artificial intelligence and its application to policy, especially where it affects us, or even marginalized and underrepresented populations who may not necessarily have the expertise or the voice. So the purpose of this lecture is to introduce learners to the basic components of artificial intelligence. This is by no means exhaustive. So this is fairly high level. So if any of you are computer scientists or data scientists, I'm not going to be able to discuss it to the level of detail that, you might already have a grasp of. I'm trying to use in as much as I possibly can non-technical language, but in many instances, when you're working in the documentary heritage profession, you're working with people, particularly if you want to deploy artificial intelligence within archival or documentary heritage processes, you're going to be working with people that may end up using technical language. So I think it's good to have a certain level of technical language under your belt so that, you're not necessarily have the blinders pulled on you. But equally as well, for those of us that work in the public sector or that may work in educational environments, post-secondary institutions where a lot of researchers are creating bespoke AI, and what does that mean from an acquisition point of view, and then what also does that mean from a policy point of view? And so what are the types of questions that we can start asking when we're dealing with researchers or decision makers? And we'll really examine different types of artificial intelligence, how they are constructed, trained, and operated. My focus really is going to be on machine learning because that is the type of technology that more often than not, as documentary heritage professionals, we will be dealing with, particularly off-the-shelf machine learning software. Sometimes we'll be in the very privileged position to be able to work with computer scientists and mathematicians to develop artificial intelligence software, but most of the time we're going to be dealing with off-the-shelf materials. So a definition, I'll be looking a little bit at it, I think, as a definition of artificial intelligence. I think it's always good to have sort of a starting point when we talk about these types of things. Types of machine learning, as I said, the focus really for me will be on machine learning. I'm not going to really discuss in great detail neural networks at this point. I think partly, as I said, because those are not necessarily the types of technologies that we would be able to access as documentary heritage professionals. There are three types that I will discuss, which are supervised, unsupervised, and reinforcement. Sort of looking at the basics of machine learning. So these are really, again, for off-the-shelf commercial software. So we'll be talking about vectors, probability, accuracy, and recall. Accuracy and recall factor into any type of AI, but vectors, particularly when you're dealing with off-the-shelf commercial software, are more present because off-the-shelf commercial software tend to have a lot of statistical models sitting behind them as well as vectors. It's not to say you're not going to find that in sort of deep neural networks, but there may be different types of machine learning models that may be sitting behind that, not simply those based purely on statistics and vectors. I'll talk a little bit about types of algorithms. Again, I will focus primarily on text mining algorithms because that's really what we're working with within the profession. And I'll talk a little bit about some of the research we did at National Archives and some of the things to think about and questions to ask when you're engaging with these technologies, particularly as a tool to facilitate archival appraisal and selection. But also, I think more broadly, types of questions we need to think about when we look at text mining machine learning algorithms with a very sort of light touch look at different types of deep neural networks. So I'll present you different types of models, but again, that could be a whole nother presentation just on deep neural networks. So I've asked, I just want to sort of get a sort of sense of the room and what your knowledge is on AI. So if you look at your Zoom, you should have a pop-up and you should sort of be able to tell me what is your level of knowledge regarding AI. So I'm just trying to get a sense of the room and where people are at. Okay, it looks like we have 80%. There's 5 of you outstanding, so I'll give you just a moment. So it looks like most of you are at a 2. So anybody who's at a 4, as I said, this is not going to be a highly technical presentation. So just to manage expectations a bit about the type of discussion that will be, or the type of presentation that'll be had here. And because there's a lot of people within the documentary heritage community that don't necessarily have a lot of in-depth knowledge. I think that's where the majority of the people in the group are sitting. So I'm going to give it one more couple seconds and then I'm going to close it down. So we're going to stop that and I'm going to share the results. So you can see that most of the people, 50% are at a 2, which is kind of what I expected. But like I said, for anybody who's at a 3, you might not find this presentation particularly meaningful, but, I'm happy to take any questions at the end. And I'm also not, I haven't actually done vector training. I've read a lot about it. What we primarily dealt with and what I have dealt with has been off-the-shelf commercial software, which is not very advanced at all. It's pretty basic. And a lot of the AI I was dealing with when I was in government was, it was sometimes challenging to get a level of oversight regarding the training of the algorithms. So, like I said, you're not going to get deep, detailed information during this presentation. Highly technical information, that is. Okay, thank you, everyone. That was really helpful. So to start off with, artificial intelligence can be defined in many different ways. There's no real, I would say, agreed definition that I can find. It sort of varies. It's always a variation in the theme. But I think the most encompassing definition is as follows, which is it is a wide-ranging branch of computer science and mathematics concerned with building smart machines capable of performing tasks that typically require human intelligence. So I would say that based on my experience, absolutely. I think AI has a lot of potential. I think there is sometimes when we look at artificial intelligence, a lot of perhaps overestimation about the capabilities of the machine. I think that they can be applied in circumstances and under certain conditions to great effect. Speaking as someone who works in the documentary heritage profession, the amount of digital information that as archivists and as librarians and others that we have to process, and even in the data sciences as we look at big data, it's too big, and we need these types of machines to help us. I think the big sort of question is, how do we apply these to best effect? Understanding the limitations of artificial intelligence, and also trying where possible as well to compensate for levels of bias that might exist, or asking the right questions to be able to address questions of bias. Machine learning is the use and development of computer systems that are able to learn and adapt without following explicit instructions by using algorithms and statistical models to analyze and draw inferences from patterns in the data. And then finally, neural networks is a computer system modeled on the human brain and nervous system. And neural networks really sort of are overlays of different algorithms operating at the same time. And deep neural networks are really a number of different neural networks that are operating in conjunction. A good example of a deep neural network would be facial recognition software. So deep learning is a type of machine learning based on artificial neural networks in which multiple layers of processing are used to extract progressively higher levels of features from the data. But as I said, the main focus today will strictly be on machine learning. So there are different instantiations of machine learning. So there's supervised, unsupervised, and reinforcement. So supervised is really about starting to map the data and get a sense of what's inside the data, because, and this is something we did a lot when I worked in the UK government with some of our departments and their legacy data sets, because they had much too much information. And because of high staff turnover, they didn't always know what was inside the data. And so some off-the-shelf commercial software products will help you get at least a very high level understanding of what may be contained in the data, such as format, date. And then you can also sometimes train these machines to varying degrees to identify different concepts or different entities or regular expressions, which are things like social security numbers, so regularly expressed number, sequences of numbers. Unsupervised is really about having the machine do the work for you. So it's about developing classes within the record set that you're, or the information that you're looking at. You can't lose sight of the fact that in unsupervised, it has already gone through a supervisory process to be trained. It's just that what it's doing then is based on its original training, it is rendering the material in different classes. And then reinforcement is about mapping and then also creating classes of records. And I'll talk a bit more about that when we look at reinforcement training. So supervised is a task of learning a function that maps an input to an output based on the input-output pair. So that's a very fancy way of just saying, I want to find an apple. So I'm going to identify all the material that says apple in it. And then I'm going to teach the machine to predict within the data set that I've fed into it. I'm going to ask it to predict and identify correctly the majority of the entities that I've identified as apple. So if I looked at this from the perspective of having trained for appraisal and selection, so what I was doing in some instances, it was having the machine firstly tell me some basic information such as date and format, and then I would tag information like names and things like social security numbers, dates of birth, date, and then I would train it to look for different instantiations of those terms or dates, because dates and digital records, you would think it would be fairly straightforward, but those of you that have probably worked in digital preservation and with digital records know that's not the case. That dates can be expressed in many different ways in digital records. They can be the dates in the metadata, so the information about the Word document or whatever it is you're looking at. The date can also be, and there can be several different dates attached to a document. So it could be the date it was created, the date it was last modified, the date it was printed. You know, there's many different dates that sit there under that in the metadata. And then there's the date that can be sometimes in the actual title of the record, and then the date that's in the record. So, and the date in the record can be expressed in many different ways. So it could be date, the month written out, the year, sometimes fully with 4 digits, sometimes with 2 digits. Sometimes it was month, it was day, month, year. Sometimes it was day, month, year. So we had to train the machine in a supervised learning environment to identify all these instances. So supervised is a lot of work. Supervised requires you to physically, with off-the-shelf commercial software, to actually go in and tag different things that you want the machine to look for. What becomes important when you're doing supervised is, what is the basic question you are starting with? What are you asking the machine to do? And this becomes important throughout the process of artificial intelligence, whether you're dealing with simple machine learning models or whether you're dealing with deep neural networks. Because the question, it's always, whenever anybody who's done advanced degrees, the research question becomes fundamental. The problem that is trying to be solved becomes fundamental to assessing what you're going to put in and how you assess the output. And so when you're doing supervised, machine learning as an archivist, it's a lot of upfront work, because you have to, tag a lot of information that you need the machine to automatically identify. And then you have to keep retraining the machine until you get it to a level that you feel comfortable and happy with. And one thing I always say whenever I give presentations about machine learning is it will never be 100%. So we need to disabuse ourselves of the notion of perfection when we look at machine learning. It will never be perfect. We are not perfect. Machines are created and trained by humans, so they aren't going to be perfect either. They can create and identify, or rather identify more information than we can, than if we're just sitting and staring at a computer screen. There's documented research that looks at how humans interact with text, and how after a certain point, the levels of attention and detail in looking at text records decreases as you go through a large volume of information. Whereas machines don't have that issue. They consistently are looking for the same thing all the way through. So coming back to supervised is that it does, though, take a lot of work, because you have to sit there and you have to identify every single piece of information that you need the machine to figure out. And also, there is not a vendor on the market that's going to give you a straight answer. And even I've asked even data scientists and computer scientists, what is enough information to be able to train, particularly if you're doing supervised machine learning, to be able to train a machine to identify different tags. And they will give you different numbers, and they'll just say the bigger the amount of information or data you have, the better it is, which is completely unhelpful. But it is something to be mindful of as you're doing supervised data, because it does require a lot of upfront work, just as much as when you're actually building and training a machine learning model, because you have to tell the machine. It's much more technical, because what you're doing when you're working on it as an archivist is that you're just highlighting different pieces of information and saying, here's and sometimes what you'll do is you put it in an Excel document and feed it into the machine so that it can automatically identify it. Whereas if you're a computer programmer, you're assigning numerical values to information, which I'll get to a bit in vector analysis, that sort of parses out the information on a graph. So it's still a lot of work, because also you have to remember in text documents, again, because that's what I'm talking about as an archivist, is that not everything is spelt the same. We already have American versus, British spellings. We have misspellings. So even when you're training a machine, it's factoring in that not everything will be perfect, even at the part of even from the point you're building the algorithm to the point that you're then training a pre-existing algorithm as an archivist. Then you have unsupervised, which is a type of machine learning in which the algorithm is not provided with any pre-assigned labels or scores for the training data. And as a result, unsupervised learning must first self-discover any naturally occurring patterns in the training data set. I would say that there is a level of self-discovery by the algorithm, but it's already been pre-trained to identify certain classes of information. So I would add to that definition that, you know, there's already a level of supervised machine learning that's happened. And with a lot of the systems that we were working with when I was in government, when I was in civil service, we had some vendors who were saying, yeah, it can do concept analysis, which is what you get a lot of times when you talk about supervised machine learning. There's clustering and categorization. And so categorization really was around the different concepts that you could find within a set of records. But again, it's been trained to identify these types of concepts, these types of notions in a pre-existing fashion. So it's something to be mindful of when we start talking about that. And then clustering is around if you have certain forms. So it'll identify records based on sort of, I use this specific type of form for, I don't know, reimbursement requests, for example, and it will extract those out and be able to identify those. So I would say that those are the two main models that you will find that are openly available and accessible in off-the-shelf machine learning software that we as archivists and documentary heritage professionals can get access to. More often than not, these will exist in things like e-discovery or data analytics software. So you're going to get a level of unsupervised depending on the software you're using, and a level of supervised. It's just varying degrees. They all kind of do the same thing. One thing I'm starting to look at now as an archivist is reinforcement learning. Is a type of machine learning technique that enables an agent to learn in an interactive environment by trial and error. Using feedback from its own actions and experiences, the machine learns from its mistakes by receiving new data and capitalizing on existing training data. So it's a very complicated way of saying that the machine, unlike supervised and unsupervised learning, it uses the base data it has, but then continues to learn by itself based on feedback it's getting from the operator. So for example, it's used a lot in AI gaming. So, and it's also used in robotics. I think a really good example of types of reinforcement learning are things like self-taught robots. So this is a really interesting article by Diana Kwan. It was in Scientific American in March 2018. In this instance, they were looking at robots, and they were programming the robots to do basic language acquisition, sort of a toddler's level of language acquisition and sensory acquisition. And the interesting thing that they found out, because they had exposed two robots to the same conditions, to the same environment, but the robots actually reacted in different ways. And so, and this is a perfect example of reinforcement learning, where the environment in which the robot exists and the type of information and how it's processing that information based on the base level of information that it was already pre-programmed with can influence the outcome. The reason I think this is more interesting for archive, from an archival perspective, is that the types of information that we are dealing with as archivists, as documentary heritage professionals, is not static. You know, supervised, unsupervised machine learning presumes that the information has a level of stability to it. Has a level of repeatability in terms of the content and the results. And that is not the case at all with archival information. If we look strictly, for example, at appraisal and selection, so figuring out what to keep and what to throw away, that changes over time. There are different events that occur over the space of different times. There are different anniversaries, there are different crises. There are, different, big research that, your government or institution might be involved in that we need to make sure that we capture. And that isn't static. There's no one concept that you can assign to a specific event. or a specific, function. For example, in governments, functions move and change, and sometimes we call different functions different things. And so we need something that's a lot more flexible so that we're not constantly having to retrain the machine every time we get a new set of information for what is appraisal and selection and sensitivity review. I also think over time, and I think this is reinforcement learning is becoming more, is also used a lot in the financial sector to help predict financial outcomes. And I think when we look at this from a policy perspective, this becomes important regarding what are the financial systems reacting to, particularly if it has an influence on economy, jobs, our own viability in terms of as individuals, economic viability. And so it's important that we are mindful both from a professional perspective, but also from a citizen perspective about how these machines are being trained and the environment to which they're reacting to. I think what the Scientific American article shows us sometimes is that it's not always immediately apparent what part of the environment that a machine may be reacting to in a reinforced learning environment. And so I think that that is where the difficulty comes in applying some of these more, I would say, advanced machine learning technologies, both in terms of our profession, but I would say also from a policy perspective as well. But it is something that is, for me, a lot more interesting when I look at this from an appraisal and selection point of view. I don't think at this point it has been widely used in government policy decision-making yet. I think it may eventually become more widely used as governments need to react more quickly to different sectors, different issues. It could eventually be rolled out in healthcare and epidemiology if we just look at the COVID epidemic now. So it's something that we do need to at least keep an eye on as a profession. But I think as a citizens and as a profession, but I think it's something that we need to shift. Right now, we're talking just very generally about artificial intelligence within the profession. And I think that I would like to pivot the profession to start looking at reinforcement learning rather than simply focusing on basic commercial algorithms that may be out there. I think they're useful in the short term, but it's something we need to be mindful is that we always need to be looking ahead with these technologies. We can't just be satisfied with what we've got in front of us. And that's the same when we look at this from a policy perspective. It's like we constantly need to be looking 2 steps ahead about what's coming down the stream. I think one of the members of the advisory board for HIRA very rightly said, we need to start even looking ahead to quantum computing and the impact that this will have on machine learning as well as its application in the policy environment. So basics of machine learning. So we're getting into a bit more of, if you will, the nitty gritty of what makes at least a lot of the off-the-shelf commercial software tick. So as lay people, I think we need to understand when we consider commercially available machine learning algorithms, we need to be aware that vector analysis or linear algebra definitely plays a role in these machines, statistics and probability. Now I say don't panic, because a lot of us in the archival profession, and I think in the documentary heritage profession, have our war stories from the mathematics classes we all attended, or the trigonometry classes we all attended, calculus classes. So I think that I'm not saying we have to have a deep understanding of the maths that sits behind this, but we have to have an understanding, I would say, in terms of how this impacts how machines are trained, and then how this impacts the output. So from a policy perspective, as well as from how we deploy these technologies in our profession perspective. And each of these, as I said, plays a role in the mathematics of machine, or in the operations of machine learning. The key question that needs to be remembered is, what is the problem that the algorithm was trained to try and address? And I reinforce this over and over again, because we can talk about vector analysis, we can talk about stats, we can talk about probability. Machine is just doing what we're asking it to do. It is still just a tool. And a lot of the this goes as well, I would say, for neural networks, it's that they can't assess every variable. They can't assess everything. And so we need to be mindful that these are still machines and they can only do a set number of tasks, which are fairly simple. Even if we look at neural networks and we look at facial recognition software, it's doing one task. It's recognizing our face. It's not recognizing, you know, whether we're happy, whether we're sad, what type of environment are we in, how does the environment affect how we, you know, how we look, the lighting, how does that affect things? And it's still making statistical analyses and probability. Like you look at some of the discussions around the application of deep neural networks to facial recognition software, and you have everything from the bias of the original data and the accuracy, the probabilistic accuracy of the return of that algorithm when it's dealing with people who are not Caucasian, because it was primarily, a lot of them were initially just trained on people of Caucasian origin, Caucasian descent. And so the levels of probability it has for other ethnic groups decreases depending on what the training set of the data is. So that, again, we talk about bias when we look at this. So, you know, they seem really complex. They seem really difficult to understand, but in reality, they are, I wouldn't say simple by any stretch of the imagination. There are complex mathematical models and statistics probabilities that sit behind it. But I think that we need to be mindful that what they can do is still, at this point, quite limited. And I know one of the questions I get a lot when we look at machine learning in a policy environment or in a professional environment is, will it make me obsolete? Will it make my job obsolete? Will I lose my job? These were the same questions people were asking themselves when personal computers were deployed in the workplace. It's not going to have that effect on us, not for a very long time. It may change certain sectors, but it's not going to make us redundant. And so I think what we need to do is we need to set that fear aside. And what we need to understand is what's making it tick. You know, it's like, I think of the movie Hidden Figures, where one of the ladies figures out how the IBM machine works and ensures that her group, her staff that sits under her at NASA is able to then pivot to a computer environment. These computers still need humans to help them work. And I think the main thing we need to remember as archivists, documentary heritage professionals, even those that are interacting around machine learning from a human rights perspective, is we just need to understand how these things tick so that we know how to ask the right questions, we know how to deploy them properly, and from an archival perspective, we know how to capture them. So, vector analysis. So statistics, we all know, is about collecting, analyzing, and inferring outcomes from the interpretation of numerical data. Vector analysis plays a role in different parts of the machine learning process and deep learning process. Our focus is really on the input vectors because the input vectors influence what we eventually get at the end of the process. And then finally, probability is trying to predict the likelihood of an outcome or influence the likelihood of an outcome, often from imperfect or incomplete data. And I think this is vitally important to remember, that more often than not, we are dealing with imperfect and incomplete data, because the types of questions we may be asking may be inherently complex, or the data sets in order to train these machines, because to train any type of machine learning, whether that's basic supervised machine learning off the shelf to huge neural networks, is you need vast amounts of data to do it in order to get a level of accuracy that is or precision and recall, more often is what it's called, that is over 50%. So anything that's 50%, you go back to the drawing board if that's your precision and recall, because it means it's no good. It means it's not actually making a determination. So vector analysis, what vector analysis is that effectively we need to remember that machines, these are machines, and the only way they can understand the information that we are giving to them is by rendering it into a numerical value. So this is where we get into what if you recall, some of you, maybe your algebra classes, X and Y axes. So what it does is that it assigns a numerical value, or rather the programmer assigns a numerical value to something. And then it teaches, it's a piece of a piece of code that then says, you know, I want apples to be rated at 2. I want, you know, oranges to be rated at 5. And I want lemons to be rated at 6, for example. And so what it ends up doing is based on your what you've assigned in the code, and then how you put the information in. So you've got a training data set, and you clearly identify this is apples, this is oranges, this is lemons. And then you go back and you progressively train the vector by playing with the code in the background so that it properly identifies the different terms. And this is where the probability comes in and the statistical modeling comes in, because you may want to assign and say, well, if I have, you know, I have a 60%, I want to sort of cluster this, and the probability of assigning that all these are apples. And then that's where the probability comes into play, because it will then start to identify, once you've moved it on to another data set, a non-trained data set, that's when you can begin to identify whether or not the vector is working. And it's the vector, effectively, along with the probability of the result, that essentially influences the outcome of the machine learning software. And so this is where, at least understanding that vector analysis, and that it effectively renders a word or a concept or an idea into a number, and the probability that sits behind that in terms of accuracy then influences the output. So what you get at the very end of the process. So if you have, let's say you're looking for peaches, you're not going to find that, because that's not what the vector was trained to identify. It was trained to identify, you know, apples, oranges, and lemons. But if you put peaches in, you'll still get a value. Like, you'll still say, I want to find stuff with peaches, and it still give you a result, but it's not an accurate result. So it's something to be mindful of as you look at machine learning algorithm software. And this is primarily what you're going to find on off-the-shelf software, off-the-shelf e-discovery software. This is pretty much what sits behind it. And I think that there are questions as we look at this when we're talking with service providers about, well, what was the basic training data set that you used? And, you know, what type of vector analysis did you do? How did you kind of try and assign the probabilities to get a certain level of response? They may not answer that, because when you start getting into vector analysis, it actually becomes proprietary, because the software will have been trained in a specific way to arrive at a given result, and how the vector was built. And sometimes even the training data set, although more often than not, a lot of these commercial service providers will be using public data sets because they're the biggest ones that they can get their hands on. They may not want to be transparent about that, but sometimes you can get at least a discussion about how the vector was trained and how then the system is arriving at those results. So questions to ask yourself as you look at the outcomes of machine learning algorithms. How were the vectors trained? What was the training data set? What was the algorithm trained to do? And again, that becomes a really important question, because that will influence how the vector was built. It will influence what the vector is looking for, like how effectively what the machine is looking for based on how the vector has been programmed. And is it the right algorithm to use depending on the question that you're asking? So if from whether that's a policy perspective or whether that's the perspective of as an archivist or documentary heritage professional, it's how closely does the question that the algorithm was originally trained on align with what it is that the policy problem is, or the appraisal and selection question is, because it'll influence other things that you may need to look at, or other things that might need to be asked to get a really good overview of the situation. Ostensibly, how the vector is designed will affect precision and recall, especially if you're using it, you're not training the original, you're not training the software from the beginning. It will affect the type of precision and recall you will get if you're using off-the-shelf commercial software. And so precision is what measures how many times the model correctly predicted an outcome over a number of possible correct and incorrect outcomes. So essentially what precision is effectively saying how many times has it identified apples and oranges. Whereas recall measures how many times the model correctly predicted an outcome. So how many times has it actually correctly identified apples? And then probably the most meaningful score, though, when we're talking about precision and recall, is the balance. So the F1 score is the balance between precision and recall, which provides a probability of correctly identified outcomes by the algorithm. I think what you need to remember, even in precision, though, is that in precision, you may have the machine has incorrectly identified apples. It's called a false, I think I've got it in the next slide. No, I don't. It's called a false positive or a false negative. So it's essentially said this is negative when it should be positive, when it should be identified as apples. And that's where you need to look at why is it misidentifying the information. Sometimes the reason it's misidentifying the information is because of the statistical model that sits behind it. It could be because of the way the vector was trained. And so sometimes you need to then re-input that information into the machine learning algorithm to try and see if you can figure out why is it not correctly identifying this version of apple. Is it because it's misspelled? Sometimes that's what the issue is, versus this version of apple. And that's where having a good understanding of your training data set becomes really key. Even not simply also the data set that you marked up, but then the sort of blind data set that you're going to put in to test the model. So you need to have a sense of where the instances of apple may reside in that data set so that you can have a look at why is it misidentifying that information. But when you're dealing with commercial providers, it's often important to have just a sense of these types of terms, particularly the F1 score. I think it's important to ask because the F1 score is the more accurate score that gives you a good understanding of how well the machine learning software is performing. And from a policy perspective, it's the question to ask about, just how accurate are the results that you're basing your decision on. So just to give you a sense of how this is more, you're dealing with a piece of machine learning software that has already been trained. So you normally have different types of data that may be plugged into the model. So you might have Word documents, you might have data sets, you might have tweets. And then you've got another, you've got that piece of code, that vector analysis that is working in the background, parsing through all that data. And oftentimes what ends up happening is all of that data creates things like visualizations, which makes the outcomes of machine learning software from a policy decision perspective a lot easier to understand. The problem is that if you don't understand or you don't know what's sitting behind that and how how the data was identified, how the data was cleaned, and that's another important thing. Even when you look at vector analysis, how was the data cleaned as the vector was being trained, can have a huge impact on the outcome. And also what types of training data sets were used, from vector analysis all the way through to using an off-the-shelf commercial piece of software, because that data can have a huge effect on the outcome of decisions, especially if it's biased, especially if it hasn't taken into account certain variables, or, I think particularly around socioeconomics, that's usually a pretty big one. If it hasn't taken account, socioeconomic areas that may be underdeveloped, and how does that then impact on the results? Because then this could impact on, who gets money, who doesn't get money, who gets resources, who doesn't get resources. It could impact as well from a perspective, a documentary heritage professional, of what records get selected and what records don't get selected, and how does this have an impact potentially on how people understand history. And I think we can't lose sight of the fact when we look at these types of machine learning software. So not all algorithms are the same. So I focused here on text mining algorithms and just text analysis in general, and different types of text mining that you may come across as you're working as an archivist, because that, as I said, or as a documentary heritage professional. And so you can see that there's information retrieval, you've got information extraction, concept extraction, natural language processing, clustering, classification, web mining. Again, you need to be mindful that each of these has their strengths and weaknesses. It also depends what it is that you're looking for. I'm looking specifically, say, at concept extraction, so co-location, sentiment analysis, word association. That can be really helpful, but it's not a silver bullet. So I think about this from the perspective of sensitivity review, because we had a lot of vendors that were telling us, we do sentiment analysis. The co-location of the words can automatically help you identify sensitivity. It's not the case at all. So you just need to be mindful about how is the algorithm, and you can see the different algorithms on your right-hand side. How are those algorithms potentially deploying these technologies? How have they been trained? And so how useful are they to assist in some of these processes? Sentiment analysis from a sensitivity review point of view, it wasn't helpful at all, because they anticipated that because something was a negative sentiment, that it was sensitive. So there are certain associations that some vendors make that are perhaps incorrect. And I think you could spin that out into how policy decisions sometimes are made. There are sometimes correlations that don't necessarily make sense, or there are assumptions in the correlations that effectively mean that sometimes decisions aren't properly being made or properly interrogated before arriving to the final decision. Because simply saying that sentiment analysis means that something, or a negative sentiment, it means that something is automatically sensitive, is not necessarily the case. And again, so this is an idea of different types of neural networks. I know we didn't have a chance to really discuss this in great detail, but it's just to be mindful that you're not going to always be dealing with the same algorithm all of the time. When we look at this, whether it's from a policy perspective or whether it's from the perspective of an archivist using and deploying these technologies, is that you may have to layer different types of algorithms, different types of commercial pieces of software, or in this cases, different types of algorithms in and of themselves to create a deep neural network. It's not necessarily that one thing is going to solve every aspect of the question. It might solve one component of the question. And so it's just to be mindful. So in terms of conclusion, you don't have to be an expert in linear algebra, statistics, computer science, or data science. I think it's important to have a grasp of what is going on in the background when you're doing machine learning. So vector analysis, it's about how the information has been plotted effectively on a graph, and how the probability of what is determined to be an apple, an orange, or a lemon, how that probability is set, and how that probability then impacts on the outcome, how the assessment, the prediction made based on the model impacts the outcome, and the accuracy of the outcome, and the precision and recall. Sorry, I misspelled that, but what is the problem that is trying to be solved by using machine learning? Because that again, as I said, that is really the key question as we look at this from a policy perspective, from a perspective of how we deploy this in our tech, how we use commercially available software in our practice, how we train that software as well, and then also in terms of when we're looking at this from algorithm as a record, what do we capture? Like, what is the relevant information that we need to capture? What was the problem that they were trying to solve? And so therefore, what were the data sets that we need to capture as part of capturing the whole algorithm, and how the algorithm arrived at its outcome? And particularly when we look at this from a policy perspective, where a government department has developed its algorithm or its deep neural network, that becomes particularly important as an archivist, because the vector analysis process, all the documentation around that needs to be captured. The original and all the instantiations of how that vector analysis or how that code was developed, and the statistical models that sit behind it, along with the outcome and potentially other data that may be put into it to continue refining the model. So these are all really important things when we look at this as well. What was the precision and recall in the training data sets? So, you know, how well was that? How well was it when the model was originally trained? What were the results? The commercial supplier may not tell you, but it's something if you are able to ask, it's worth asking. And I think too, even from a policy perspective, like, what was the precision and recall on what, you know, they were getting in terms of the data that was being used to arrive at the decision? Was the precision and recall, you know, 90%? Was it 60%? And also, you know, what are the mitigations then that are in place to ensure that, you know, it's not necessarily the decision is not solely based on the output of the machine. We saw what happened, you know, there's well-documented instances and a lot of research on recidivism rates in the US justice system, particularly in Texas, and some of the really big issues around the bias in the original training data set, the bias in the questionnaire that was used. And I would have questions around what was the actual precision and recall? How was that assessed when those types of technologies that were being developed? I think another question is, as we talk about, you know, the fact that it's not going to be 100%, what is good enough? Whether that's from a policy perspective, whether that's from deploying these technologies in an archival setting, what is good enough for us? Because 100% is not achievable. And how do you manage false negatives? So how do you manage results where it should be, you know, it says Apple, but it's not being classed as, the machine's not identifying it properly. And like I said, it's not going to be 100%. There's going to be stuff that's going to be missed. So how do you mitigate for the risks that may remain as you're deploying these machine technologies in archival practice? Or, you know, from a policy perspective, as citizens, what are we willing to accept as terms of what is an acceptable rate of precision and recall and false negatives that may be in the data? So here's just some resources. Towards Data Science is probably one of the best resources I can recommend. They've got really great articles, very accessible articles on vector analysis, on machine learning, all sorts of things. There's another great article by Neptune.ai on understanding vectors and their application to machine learning. A bit on very high level on sort of the maths behind machine learning, precision, recall, and accuracy and F1 scores. Of interest for those of you that may be looking at examples of deploying artificial intelligence or reports around artificial intelligence in an archival setting, there's the National Archives UK just came out with a report called Using AI for Digital Records Selection in Government. Last year, the National Archives and Records Administration in the United States came up with Cognitive Technologies, a white paper. Also, the National Archives of Israel has also deployed artificial intelligence machine learning in their appraisal and selection processes. And there are several other archives that have. And this was also a big topic that we discussed in the ICA's virtual conference that took place a couple of weeks ago. So that kind of gives you a sense of sort of some of the basics behind machine learning, how it works, and just to get a sense of the types of questions, the things to think about as you're engaging with these technologies.